All right, so starting off in Unit 14, we're going to look at some slightly more advanced applications of trigonometry, and this is the first one. This is section 14.1, and the I can statement for this lesson is I can find the modulus of a complex number. So let's write the word modulus. Modulus of a complex number. We'll talk about what that is in just a few minutes, but let's do a little warm-up here. Let's talk about the square root of negative 16. So remember, when we've got a negative number and we're taking the square root of that, we've got to kind of break it up like this. We've got to think of this as the square root of 16 times the square root of negative 1, because we don't really have any way to deal with this, but we can deal with the square root of 16. So this is a 4, and then the square root of negative 1 is an I. So this is going to be 4i. And then we can do the same type of thing here. When we deal with the square root of negative 18, we can just say, look, there's going to be an I in there. So I'm going to go ahead and put that right there. And then we just need to figure out the square root of 18. So remember, this is going to be 3 times 2, pair of 3's. So we're going to have a 3 on the outside and the 2 stuck on the inside. So we have 3i radical 2 for an answer on that one. And then just a couple things that we don't want to forget. If you've got I is defined to be the square root of negative 1. That's called the imaginary unit. And then I squared is what we get when we square this. So if I were to square the square root of negative 1, the squaring would undo the square root, so we'd end up with just negative 1. So if you remember those two things about I, that I is the square root of negative 1 and that I squared is negative 1, you're going to go pretty far as figuring out how complex numbers work. So remember that a complex number written in a plus bi form, that's the way we normally write that. That's sometimes called standard form, where a is a real part and bi is called the imaginary part. Imaginary part right here. And then just a quick reminder, hopefully this is something that you've locked away at this point in your math career, your math learning, and that is, what is absolute value? So think about that for just a second. We're used to seeing like absolute value of 7, absolute value of negative 12 or 11 or something like that. They only make that a 12, so it'll look a little bit better. Okay. So what is absolute value? Well, hopefully you know this by now. It is the distance from 0. Absolute value is the distance from 0, and distance is always positive. That's why absolute value is always positive. Some people make the mistake that, oh, it just makes everything positive. Well, that's kind of true, but the reason why is that we're finding the distance from 0, and distance is always positive. So remember, when we've got things written in complex numbers written in this form right here, a plus bi, a and b, they are both real numbers. It's when we put the I on there that becomes the imaginary part. And we actually introduced these when we were talking about solving quadratics. So we ended up solving quadratics where we were taking the square root of both sides, or maybe using the quadratic formula or something like that, and we had to take a square root of a negative number. Well, it can actually be helpful if we visualize where these are on the xy plane. And the xy plane is a real plane, so we can't really graph imaginary numbers on the real plane, but it is possible to graph them on a different plane. So that's what we're going to talk about partially today. So we're going to talk about the complex plane. We can graph complex numbers on the complex plane, and it's going to allow us to see some patterns and some visualizing things that we may not be able to understand if we didn't have a complex plane. So a complex number can be thought of as an ordered pair. So instead of graphing an xy pair like we normally do on the real plane, we can graph the number a plus bi as the point AB on the complex plane. So here's what the complex plane looks like. The complex plane has a real axis horizontally, so that's kind of like our x-axis, and then we have an imaginary axis that's the vertical axis. So this is the real axis going horizontally, and this is the imaginary axis going vertically. So sometimes we refer to a plus bi as a rectangular form because we can graph it on here. So we're going to go through and we're going to graph a couple of numbers, and you'll notice that I've got a z and I've got a subscript on each one of these, and that's because we often will use the letter z to represent a complex number. So just kind of get used to that. If somebody says z equals, a lot of times they're talking about a complex number. Not all the time, but just as a general rule, we're going to use z to represent that. It just makes it a little bit shorter to write. So we're going to graph the following numbers that are already in rectangular form, and we're going to graph them on the complex plane, and then I'm just going to label them. So z1 is negative 4 plus 3i. So we'd be at negative 4 on the real axis and 3 on the vertical axis. So this one right here is z1, and I'll go ahead and label this as negative 4 plus 3i. And then we've got z2 is at negative 5, negative 1i, so we'd be right here. So, whoops, z2 is negative 5, negative I. And then z3 is at 4, negative 4, so 4, negative 4i, so 4 and then negative 4, so that's z3. And we've got that at 4, negative 4i. That's what's represented by that point on this complex plane. And then the last one is radical 3 plus I. So radical 3 is about 1.7, so we're going to go about right there. And then 1, so this is going to be z4. z4 is radical 3 plus I. And then we've got all 4 of those graphed over here, and we've got them labeled. Now, if we graph a complex number in rectangular form, we might be able to figure out how we can compute the absolute value of a complex number. So absolute value of a complex number. So let me write this one down right here. This is the first one that we did up there. This is z1. So negative 4 plus 3i. Well, negative 4 plus 3i would be over here. So I'm just going to write negative 4 plus 3i. So we've graphed that. And again, this is the real axis and this is the imaginary axis. And we want to know what the absolute value of that is. Well, if you think about the warm-up and we were talking about what absolute value is the distance from 0. So what we want to know is how far is it from here to here? This is 0 on the plane, the origin if you want to think of it that way. What we want to know is we want to know this distance right here. Okay, so I'm just going to use an R for that right there. And then the horizontal component right here, this real part is negative 4, and then the vertical part, this imaginary part, is 3. So if we were to think of this as a right triangle, we can figure this out now, no problem at all. So the R is going to be the square root of, let's see, negative 4 squared plus 3 squared. And the reason for that is the hypotenuse squared would equal a leg squared, so negative 4 squared, plus the other leg squared, which is 3 squared. Now you'll notice that it wouldn't matter if I were thinking of this as a triangle with all positive lengths and stuff like that. It doesn't make any difference because when I square this, I'm going to end up with a 16 here and a 9 here. So I end up with R equals the square root of 25, which is 5. So how would we find the absolute value? How would we find the distance that this number is from 0? Well, we kind of just use the Pythagorean theorem. The distance formula, if you want to think of it that way, and we end up with 5. So the distance that this is from 0, the absolute value is 5. Now we can kind of generalize that here. So the absolute value, or if you would just underline modulus, so this is what the modulus is. The modulus of a complex number in rectangular form is this. So we're going to make a big square root, and we square the real part, and I'm going to go ahead and put that in parentheses, plus the imaginary part squared, and it's just based off the Pythagorean theorem. So that's how we find the modulus. We normally don't talk about this in terms of saying what's the absolute value of a complex number. I just kind of did that example to kind of show you where this might come from and why we use these symbols right here. So these big vertical bars do mean absolute value. They do mean distance from 0. But normally we're going to call this the modulus. So in example 3 here, it says find the modulus of the following complex numbers. So let's just take this. So here's the complex number in rectangular form. If we put it in absolute value, that's what it means to find the modulus. And then the formula says, well, I'm going to take the real part, negative 3, and I'm going to square that. I'm going to take the imaginary part, negative 3, and square that. And then remember, we don't worry about the I here because the I is taken care of in this vertical part right here. We're just keeping track of the lengths of each one of these. So we're not going to take negative 3i and square it. We just take each one of these lengths, if you want to call them that, each one of these distances. So this is going to be 9 plus 9. So this is going to be the square root of 18. And we actually did the square root of 18 up above. That's a 3 and a 3 and a 2. So the answer would be, 3 square root 2. And if I were to look at where that is, negative 3, 3, negative 3, 3 is right here. So I'd have negative 3 here. I'd have 3 here, and then what we're talking about is this distance right here. We'll call that an R. We're talking about that distance right there. And you might recognize that, hey, if these two are the same length, this has got to be a 45, 45, 90. So to go from a leg to a hypotenuse, we would just multiply by radical 3. So it works just fine on that one. I'm going to go ahead and change colors for this one here. So we're going to take the real part, radical 3, and we're going to square it. The imaginary part, which is a 1, and we're going to square that. So squaring the square root of 3, I get 3. Square 1, I get 1. So this is the square root of 4. So we end up with 2. So the modulus of this complex number in rectangular form is 2. And let's see if we can locate this one. This is the one that we graphed up above. So we're talking about this distance right here, and we've got a radical 3 here, we've got a 1 right there, and you might recognize this because this is the short leg on a 30, 60, 90. Anytime the relationship between the two legs on a right triangle are multiplying or dividing by a radical 3, you've got a 30, 60, 90. So that means we double the short leg to get the hypotenuse, so this would end up being 2. So that's basically how you do that. And again, really all we're working on is just kind of getting a sense for how the modulus of a complex number works. But let's flip this over and take a look at the other side. All right, it says find the modulus of each complex number. So again, we can just set this up and we can say, hey, I'm just going to take the real part. I'm going to square that. I'm going to take the imaginary part. That's -2. I'm going to square that. So I get 16 plus 4. So this is the square root of 20, but that's going to be 2 times 5. So we end up with 2 radical 5 here. No need to picture this. I suppose if you wanted to, there's nothing really special about the relationship here. 1, 2, 3, 4, and then down 2, so it would look like this. This is the complex number that we're talking about on the complex plane. But again, no need to actually draw that. We're just interested in what the modulus is. So we've got that. And we'll take a look at the next one. So again, this is just going to be the square root of the real part squared plus the imaginary part squared. So this is going to be a 4 plus 9. So we get the square root of 13, and there's nothing we can do to simplify that. So we're done. So the modulus, and just so you know this, the plural form of the word modulus, so we don't say moduluses, we say moduli. So the modulus of a complex number can be thought of as a length or a magnitude of the complex number. So we've kind of used an R for kind of like radius. The length, kind of thinking of that as the distance, like the absolute value. But we could also use the word magnitude here. And this is very similar to the magnitude of a vector. So remember back when we dealt with vectors, so this is what a vector is. A vector is a quantity that can be measured as a directed line segment that has both magnitude, so we'll write the word magnitude and direction. So you'll remember, this is example 5. It says find the magnitude of the vector v. So notice we've got v with the little kind of harpoon arrow over the top of it. And notice that we've got the angle brackets on this. So what this means is, this is very different than just graphing the point 2, 3. So we can graph vectors on the real plane. So we'd go over 2 and up 3. So I'm going to put a dot right here. This is the vector v. The vector v is this entire thing. It goes from the origin to here. The length of this represents its magnitude, and then its direction, it's heading off in this direction right here. We could also measure that a couple of different ways. We could come up with an angle and all sorts of things. But this entire thing, that is the vector. So this is the vector 2, 3, and the angle brackets kind of denote that. And there is a difference between these two things. This one can only be graphed on the complex plane, whereas this one, again indicated by the angle brackets, that can be represented on the real plane. So again, vectors and imaginary numbers are not exactly the same thing, but they do have some similarities, and we're going to kind of exploit and look at some of those similarities in the next couple of sections. So go ahead and do the self-assessment here. Hopefully finding the modulus of a complex number is pretty easy at this point, and then good luck on the assignment.